In the world of aerobatics, a pilot wants to do interesting maneuvers for the public. And so one of the things they like to do is fly inverted. In the early days, aircraft like this had just your basic airfoil, in which the air flows over the top of the wing and the lift is provided from below. So the plane can fly along and do turns and things like that. However, if you want to fly inverted, when you turn this plane over, you're losing the lift with this particular airfoil. A symmetric airfoil has a curve on the bottom as well. And so that will allow the plane then to continue flying in an inverted position for an amount of time. You're still creating lift because of the camber of the wing.
How does enough lift build up on the wing during that takeoff roll? And how does an aircraft actually stay in the air? Balloons and dirigibles are lighter than air, but what about the vast majority of aircraft that must generate lift through ways other than buoyancy? The key concept is aerodynamic lift. So let's talk about the fundamentals of what happens when lift is generated. We'll have to be careful with our discussion because there are a number of pitfalls that we could fall into that would lead us to an incorrect understanding of the physics of lift. So let's begin. Fundamentally, the lift force is due to a difference in air pressure acting on the surface of the wing. The bottom of the wing will have higher pressure than the top side, resulting in a pressure imbalance that acts on the surface area of the wing to lift the aircraft up. Pressure can be defined as force per unit area. So regions of relatively high pressure will produce higher force. Here we see the pressure distribution on an aircraft in flight. High pressure is denoted by red, and lower pressure is denoted by blue. The pressure on the vehicle changes because the pressure of the air changes as it flows over the body of the aircraft. The net force acting on the aircraft is determined by the pressure difference acting in a particular direction. There must be low pressure on top of the wing and high pressure on the bottom. All that matters is the difference in pressure between the two. But let me be clear, there is not a vacuum on the top of the wing. Nor does the pressure on the bottom surface of the wing have to necessarily be greater than atmospheric pressure. The key principle is that there must be a local difference in pressure between the upper and lower surfaces. The net effect of that pressure difference acting over the surface of the wing is what produces lift. There's a great way to illustrate the effects of pressure through an everyday example. Imagine putting your hand out the window of your car while you're driving down the highway. Now, starting with your hand parallel to the ground, incline your hand at a slight angle to the wind with your palm slightly exposed to the oncoming wind. If you do this, you'll experience a strong force acting on your hand. This is due to high air pressure acting on your palm and relatively low pressure on the back of your hand. Simply put, the air is pushing harder on one side of your hand than the other, and you feel a powerful force that results from the pressure difference and lifts your hand up. These pressure differences play an integral part in generating lift. Okay, that now leads us to a follow-on question. Why is the pressure higher on the bottom surface of the wing, or on our hand in this case? And how can we design a wing that will give us the pressure distribution that we want? The best way to examine these questions is to look at the airflow around a wing section, using a wind tunnel. Now, a wing section is essentially a two-dimensional slice or side view of the wing known as an airfoil. Now, when an airfoil is mounted in a wind tunnel, we can inject streams of smoke into the flow upstream of the airfoil, allowing it to carry downstream and flow over the airfoil surface above and below it. The entering streamlines are all straight and parallel, indicating that the flow is of uniform velocity and undisturbed. But as the flow approaches the airfoil, it senses the obstruction and must flow around it. So the streamlines begin to diverge above and below the surface of the airfoil to flow around it, accommodating the presence of this body downstream. There's one specific streamline that divides the area into a segment that flows above the airfoil and a segment that flows below the airfoil. Flow along the dividing streamline, exactly on it, will flow directly to the leading edge of the airfoil and stagnate there. This is called the stagnation point, because the flow decelerates along that streamline until it reaches zero velocity, right at the airfoil surface. It is the only point ahead of the airfoil where the flow decelerates down to zero velocity. Streamlines above or below that stagnation streamline will flow around the airfoil surface to accommodate the presence of the body, but there will always be one streamline connected to a stagnation point. As you might imagine, from the thought experiment of putting your hand out the window of your car, the pressure at this stagnation point is fairly high. Thus, we would prefer to have that stagnation point located on the lower surface of the airfoil. This will give us elevated pressure from below, which will assist in producing lift. The presence of this stagnation point and its associated high pressure is a start, but how do we generate lower pressure on the top of the airfoil? This is done as the flow streamlines curve out of the way of the airfoil and move smoothly above it. The streamlines will tend to follow the general curvature of the airfoil all the way to the trailing edge. The key to producing lower pressure on the upper surface is in the shape of the streamlines, particularly near the leading edge. Let's look at this in closer detail. Here we see that the streamlines are more closely spaced together and have much more curvature in the region right near the leading edge of the airfoil. There are two approaches that we can take in describing how this streamline curvature results in lower pressure on the airfoil upper surface. First, let's look at the spacing between the streamlines. Very close to the leading edge, you see that these streamlines are bunched together. That is, the spacing between the streamlines is reduced. There's a physical principle in fluid dynamics called the conservation of mass that can describe what is happening to the airflow in this region. The main idea behind the conservation of mass is that mass can neither be created nor can it be destroyed. To apply the concept of conservation of mass to this situation, we need to define some flow boundaries. We can think of two adjacent streamlines as boundaries across which there is no flow. The region between two streamlines is a stream tube. As air molecules flow through the stream tube, the amount of air mass flowing through the stream tube must remain constant by the law of conservation of mass. Since the flow is bounded by the imaginary walls of the stream tube, no mass enters or leaves the stream tube, the rate of mass flow at any point along the stream tube is the same. We can describe the rate of mass flow as the product of density, velocity, and cross-sectional area of the stream tube. Another name for this rate of mass flow is m-dot, which is the time rate of change of mass. It's really a measure of how much mass of air molecules is flowing through a given cross-sectional area of the stream tube in a given period of time. The principle of conservation of mass states that mass flow rate, m-dot, must be constant, no matter where you are within the stream tube, since we have said that no mass enters or leaves the stream tube. So mass flow rate can be regarded as a constant. And a constant mass assumption leads to a fundamental equation which says the product of density, velocity, and area must be constant within a stream tube. Let's simplify this equation slightly by assuming that the density of the flow doesn't change. An airplane going very quickly, say faster than about 250 miles per hour at sea level, will produce stronger density changes. But for low-speed aerodynamics, the changes in density are small enough such that they don't have an appreciable impact on the result. So we can neglect changes in density. So that leaves us with a very simple equation that says the product of velocity and cross-sectional area in a confined stream tube must be constant. We can illustrate conservation of mass by thinking of childhood water wars in the backyard. After a long, drawn-out water war with water balloons, the inevitable trump card to truly soak your friends was to secretly pull out the garden hose. Every kid learned early on that the secret to making the water travel farther was to put your thumb over the nozzle of the hose. You could easily turn a trickle of water out the end of the hose into a high-speed stream that would reach your buddies simply by blocking most of the exit area of the hose. This is due to conservation of mass. Water is generally considered an incompressible fluid, and the walls of the garden hose are clear boundaries across which water, mass, cannot cross. Thus, if you decrease the cross-sectional area at the exit of the hose, conservation of mass dictates that the velocity of the water must increase. The amount by which you decrease the area is the same factor by which the speed of the water increases. 1/2 of the cross-sectional area leads to 2 times the velocity, and so on. Now that we have a good understanding of conservation of mass, let's now go back to streamlines over an airfoil to see how they can help us understand lift generation. This is just a 2-dimensional case, so we just have to look at the lateral distance between the streamlines. We assume that there's no change in depth of the size of the stream tube. That is, the flow is 2-dimensional. Now, as the flow turns to avoid the downstream obstruction of the airfoil, the distance between the stream tubes gets smaller. The cross-sectional area of that stream tube is decreasing. From the conservation of mass, we see directly that the decreasing area must correspond to an increase in the velocity in order to keep mass flow constant. This is the key result of applying conservation of mass to this picture of the airfoil. This can explain how the local flow velocity changes around the airfoil. But we have to make one more step to link velocity with pressure. That link comes in the form of Bernoulli's equation, which is one of the most famous equations of aerodynamics and one that most people have heard of before. Bernoulli says that there is a trade-off between pressure and velocity. Let's take a look. Bernoulli's equation states that the sum of the local air pressure plus 1/2 times the density times the square of the velocity must be a constant. And in the development of the Bernoulli equation, density is assumed constant. This directly shows that pressure and velocity are inversely related. The higher the velocity, the lower the pressure must be in order to maintain the summation constant. Or conversely, the lower the velocity must be linked to higher pressure. So let's pull these ideas together. Streamlines must curve and move closer together as they adapt to the downstream presence of the airfoil. The flow is responding to the obstruction and moving out of the way to accommodate the airfoil. Closely spaced streamlines have decreased cross-sectional area, which must have higher speed flow due to the conservation of mass. And higher speed flow must have lower pressure by the Bernoulli equation. So the spacing of the streamlines is a direct indicator of the local pressure, allowing us to visually identify where the low pressure region is on this airfoil. Okay, let's now consider the other way of viewing this picture to explain why the pressure is lower on the top surface of the airfoil. This approach focuses on the curvature of the streamlines, where more curvature leads to lower pressure. Near the leading edge in particular, we see that the streamlines have a lot of curvature, giving a very small radius of curvature. Again, this curvature of the streamlines is because the flow has to go around the airfoil and is adjusted to accommodate its presence. Now picture a packet of air molecules traveling along the streamline, negotiating this curvature. This packet of air molecules experiences a centrifugal force due to the concept of conservation of momentum. This is the exact same principle that causes you to be pushed to the outside of the turn when negotiating a steep curve while driving in your car. In order to maintain that radius of curvature, there must be a centripetal force to balance out the centrifugal force that would push the air molecules away from the center of curvature. The only way to impose a balancing centripetal force on this packet of air molecules is by a pressure difference between the outer and inner side of the packet of air molecules. The outer side must have higher pressure than the inner side in order for the balancing force to be towards the center of the curvature. And if we consider air molecules very far away from the airfoil, those air molecules are at atmospheric pressure. But as we move closer to the airfoil, the curvature of the streamlines increases, which means that the balancing centripetal force acting on the air molecule packets must also increase. So the pressure on the bottom edge of each streamline must decrease as we move closer to the airfoil. So as we move from a point far away from the airfoil down to the airfoil surface, the pressure must decrease from atmospheric conditions down to some lower value. The key is this: the stronger the curvature of the streamlines, the lower the pressure ends up being at the airfoil surface. This is true wherever you have curvature of the streamlines. Aha! Now we're beginning to see how increased curvature of the airfoil can reduce the pressure on the upper surface, which then increases how much lift the wing produces. In order to fly, we want an airfoil geometry that will produce significant curvature of the streamlines. So, both spacing and curvature of streamlines can explain why the pressure is lower on the top of the airfoil. And since lower pressure acting over the area of the wing is what produces lift, we now have an explanation for lift. However, we must be careful. There are a number of pitfalls that we could encounter by relying on these simplistic explanations of how lift is produced. Let's now address head-on a very common fallacy that is often used to explain lift. The argument goes like this. We know that lift must result from low pressure on the top and higher pressure on the bottom. Bernoulli's equation clearly shows that the velocity must be higher on the top and lower on the bottom. That's all correct so far. But the explanation quickly goes astray at this point. In an attempt to explain why the velocity is higher on the top of the airfoil, many people resort to the equal time theory, also known as equal transit time. This attempted explanation observes that the air molecules approaching the airfoil get split when reaching the leading edge. Part of the air molecules go above, and the other part goes below the airfoil surface. Moreover, when we look at a typical airfoil shape, we see that there is a slightly longer distance that the air molecules must travel over the upper surface compared to the lower surface. The equal time theory mistakenly takes the correct observation of unequal distance to claim that the two pockets of air molecules must meet up at the trailing edge at the same time. According to this argument, because air molecules moving over the upper surface have a longer distance to travel, they must move more quickly in order to reach the trailing edge at the same time as the air molecules that traveled below the airfoil. The problem with this widely circulated explanation is that there is no physical reason to dictate that the air molecules from above and below must meet up at the trailing edge at the same time. In fact, we can show conclusively that this does not happen. Let's look at this pulsed smoke, where each streamline is visualized by repetitive pulsing of smoke injected into the streamlines. This allows us to track a packet of air molecules above and below the airfoil surface. If the equal time theory were true, we would expect that the two adjacent packets of smoke split by the leading edge of the airfoil to again meet up at the trailing edge. But when we follow this packet of air molecules along the upper surface, we see that the flow is not only accelerated, it is actually accelerated so much that it reaches the trailing edge much before the air molecules on the lower surface of the airfoil. Also, if we do some back-of-the-envelope calculations, we'll see that the lift predicted by this theory is much lower than what is actually achieved. For the airfoil pictured here, the distance over the upper surface is roughly 20% larger than the lower surface distance. So if the equal time theory were correct, we would expect that the velocity on the upper surface would be, on average, 1.2 times that over the lower surface, which would be the same as the free stream velocity. If we take a free stream velocity of 100 feet per second with standard sea level density and pressure and apply Bernoulli, an average velocity ratio of 1.2 would lead to an average pressure difference between the upper and lower surfaces of 5 pounds per square foot. With a 6-inch long airfoil, this gives just 2.5 pounds of force on this airfoil. However, experiments and computations of this airfoil geometry under these conditions show that the lift is actually more, about 6 pounds. Clearly, something isn't right. There are other anecdotal ways to disprove the equal time theory. For example, if the equal time theory were true, then it would be impossible for a flat plate or your hand to produce lift. The distances on the upper and lower side of a flat plate are, of course, equal. But a plate inclined at an angle, or your hand out the window of your car, definitely produces lift. Also, if the equal time theory were true, then it would be impossible for an airplane to fly upside down. But we routinely see aircraft perform this stunt at air shows, so we know that something else must be at work. Based on the lack of real physics and clear experimental evidence to contravene this idea, the equal time theory is categorically false. It is a pernicious idea that is incorrectly used to describe lift. For this reason, I'm highlighting the fallacy here so that it is not perpetuated any further. There's also a simple explanation for lift that you may hear, and while it's a simple explanation, it is not quite complete because it doesn't explain how the force is actually imparted to the airfoil. This simple theory of lift is based on Newton's third law, which states, For every action, there is an equal and opposite reaction. When a cue ball collides with another ball on the pool table, energy is transferred from the cue ball to the other ball. Newton's third law states that the action of bringing the cue ball to a rest must have an equal and opposite reaction, which is subsequent movement of the ball that has been struck. Turning to our picture of lift and the flow streamlines, we see that the oncoming streamlines are straight, parallel, and horizontal as they approach the airfoil surface. The streamlines then curve around the upper and lower surfaces such that the airfoil redirects the streamlines. As these upper and lower streamlines follow the shape of the airfoil, they leave the trailing edge nearly parallel, but in a slightly downward direction. So the presence of the airfoil redirects the streamlines from a purely horizontal direction to a slightly downward inclined direction. This action of the airfoil to redirect the streamlines results in a change in momentum, which can only be achieved by applying a force to the streamlines. And if a force is applied to redirect the streamlines, then an equal and opposite reaction force must be present, which is the lift force. So Newton's third law states that downward deflection of the streamlines must result in lift. This explanation isn't quite satisfying because it does not describe how that lift force is related to the pressure distribution. However, it is a very nice explanation for describing how we can change lift with a given airfoil shape. Newton's third law does lead to some very important insight into the aerodynamics of a wing. As we increase the angle of attack of a wing with respect to the flow, the deflection of the streamlines increases and the lift increases. This angle between the axis of the airfoil and the oncoming flow direction is termed the angle of attack. As angle of attack increases, the lift increases. This is the single most important way that an aircraft's lifting capability can be changed in flight. The pilot can pitch the nose up to increase angle of attack and the lift, or pitch the nose down to decrease the angle of attack and decrease the lift. Let's turn again to the equation of lift that we introduced in the first lecture. Lift force can be written as 1/2 times the density times the square of velocity times the wing area times the lift coefficient. The lift coefficient is a non-dimensional parameter that describes how much lift a wing produces. Another way of thinking about lift coefficient is that it is a description of how hard the wing is working to produce lift, or how much the wing is redirecting the streamlines downward. So a lift coefficient can change. It is not a constant, but it changes with angle of attack. As the angle of attack increases, the lift coefficient also increases, up to a point. Let's use the lift equation to get a sense of the magnitude of the challenge faced by the earliest adventurers who attempted to create wings and take flight. We can estimate the wing area required for flight. Based on the equation of lift, the required wing area is 2 times the weight divided by the product of density, the square of velocity, and the lift coefficient. A 170-pound person carrying a large wing might be able to run at about 5 miles per hour, and a typical wing might have a lift coefficient of around 1, perhaps weighing around 30 pounds. Pulling these values together with standard sea level density, we can calculate the required wing area as over 3,100 square feet. So for example, this would be a wing with a 20-foot chord and a span of 105 feet. If we want to get the wing smaller, we would have to have a higher minimum speed. A 5 mile per hour trot just won't do. So hang glider pilots will take off into a stiff headwind and jump off a cliff in order to get the airspeed up. If we can count on an estimated minimum speed of 30 miles per hour, 6 times our initial guess, then the required wing would be 36 times smaller, since the velocity is squared in the lift equation. This gives a required wing area of only 86 square feet, which makes for a much more portable wing of 6 by 14 feet. Or if we can only count on winds of 20 miles per hour, that would allow a wing area of less than 200 square feet, say 10 by 20 feet. Now let's use the lift equation to think about what a pilot of a powered aircraft must do in order to fly more slowly. Of course, the pilot will pull back on the power, which we intuitively understand will cause the airplane to slow down. As the airspeed goes down, however, we must do something in order to maintain a sufficient amount of lift to keep the lift equal to the weight, which is required for level flight. So the pilot must increase the lift coefficient in order to hold the plane's altitude constant. So when slowing down the aircraft, the pilot pulls back on the power and simultaneously pitches the nose of the aircraft up to increase the angle of attack. In doing so, the overall lift of the aircraft remains constant because the lift coefficient is increased while the airspeed goes down. Or let's consider what an aircraft designer can do to change the lift coefficient produced by an airfoil at a specific angle of attack. Increased curvature of the airfoil, termed camber, can be introduced. The effect of camber is to induce further curvature of the streamlines and enhance downward directed momentum. The result is increased lift at a given angle of attack, and an angle of zero lift shifted to lower angles of attack. Given this clear influence of curvature, it is awfully tempting to design an airfoil with very strong curvature in order to obtain high values of lift. However, this approach is yet another pitfall of incorrect thinking. In fact, it's such a significant pitfall we can call it a black hole. Many have gone down that black hole in their attempts to design airfoils, including none other than Albert Einstein. Yes, the very same Albert Einstein who we're all familiar with. This is a little-known anecdote from history, where Einstein actually dabbled in airfoil design. Einstein published a short paper in 1916, less than a year after he completed his theory of general relativity, that more or less describes the aerodynamic principles we've been discussing here. He put forward a summary of Bernoulli's equation, and in 3 paragraphs at the end of his short paper, described how curvature of the streamlines resulted in lower pressure at the surface of the airfoil. None of these ideas were exactly new at the time. Other authors had used Bernoulli for a theoretical understanding of lift since at least 1910, so it's interesting that Einstein would publish a somewhat redundant paper on that topic. On the other hand, civilian publication about the science of flight was mostly vanished in Germany after World War I began in 1914. Shortly after his aerodynamics paper was published, Einstein submitted a handwritten idea for an airfoil design to the German aircraft manufacturer LVG during the spring of 1917. Einstein designed what is referred to as the cat's back airfoil, which looks like this. You see a thin airfoil that curves up, and then there's a hump in the middle of the airfoil with a very short radius of curvature, and then another concave region extending back to the trailing edge. It's not hard to imagine that Einstein connected the ideas of streamline curvature to directly inform the design of this airfoil. The chief engineer of LVG received Einstein's design and actually had his team build a wing based on that airfoil geometry. World War I was well into its 3rd year by this point. A brave test pilot then proceeded to test this new wing on its maiden flight. The experience can be described as none other than a colossal failure. The test pilot reported that the aircraft performed like a pregnant duck. It was very slow to take off and mushed along in the sky, barely able to stay aloft. So what went wrong? How could Einstein, the most brilliant genius of the 20th century, come up with an airfoil design that failed so miserably, especially since he had published a paper on the theory of lift? Einstein's theoretical foundation was essentially correct, as far as it went, but it wasn't nearly deep enough. As he wrote in a letter about the failure, that is what can happen to a man who thinks a lot but reads little. He had completely neglected the effects of the viscosity of air, which directly affect how well the flow can negotiate strong curvature. It turns out that there is a limit to how tight the flow's turning radius can be. We're going to talk more about the effects of viscosity in the next lecture when we discuss aerodynamic drag. But for now, let's consider Einstein's experience as a cautionary tale about jumping to conclusions based on a few simplifying principles. Einstein himself said, "I have to admit that I have often been ashamed of my folly of those days." Our simplistic explanations of lift give us an initial understanding of what is happening, but are not sufficient for a comprehensive design. So let's review a few key points. The equal time theory is not based on physics at all. Instead, think of lift production in this way. The streamlines must deform in order to accommodate the presence of the airfoil as the air flows over it. 2 things happen. The spacing between the streamlines decreases, and a strong curvature of the same streamlines is present. Let's say these again. The spacing between streamlines decreases near the leading edge upper surface of the airfoil, leading to higher velocity and lower pressure by Bernoulli principles. And 2, strong curvature of the streamlines also results in much lower pressure due to the applied centrifugal force on the fluid packet to force the rotational motion. Lift can be tailored by altering the shape of the airfoil, introducing extra curvature or camber. Once we understand lift generated by the wing, the next consideration is to understand is drag imposed by the air. Drag leads us to consider how the flow of air around an airfoil depends not only on the wing, but also on the properties of air itself, the most important of which is viscosity, what we might call the stickiness of air.